Okay, thank you all for coming. My name is Philip Balister. I do a lot of open source GNU Radio work, software-defined radio. And I'm giving this presentation on behalf of the guys you see in front of my name on the authors list. And if you're familiar with academic work, you realize the guy that's at the end of the list did the least amount of work. So any mistakes are all my fault. And if you know this material better than I do, please point out my errors, especially when I'm talking about your products. So who am I? I've been around the open embedded community for a long time. Got into it doing software-defined radio as part of my master's work. And I am now the maintainer of a Meta SDR open embedded layer, which basically contains GNU Radio and some supporting utilities to help you do software-defined radio on your embedded devices. My paying work involves doing a lot of work with Edis Research, and I did the software load for the Universal Software Radio Peripheral, the embedded version, which is an OMAP 3-based product. I have worked as a mentor for the Google Summer of Code for people doing embedded projects with GNU Radio. Last year we had a project where a guy was looking at accelerators, the ACP port on the Xilinx Zinc processor. And this year we have an accepted project to look at this TI Keystone board. So at the very least there'll be a guy doing work on this over the summer, provided he gets a board. But he says he's got one in the pipeline, so I believe him. And basically, my job is largely to help develop technology that you can use to hack the Internet of Things. Since I'm working on mobile SDR terminals, if you've seen videos of a friend of mine, he's got various videos of him playing games with various wireless protocols, but he's got a laptop and a USRP attached via USB to it, and that's not very portable. So my interests are smaller SDRs to help you go around and do mobile software-defined radio work. So what is the motivation for this work? We're talking about doing open source work for software-defined radio, but as we're all painfully aware, when we get into the mobile space, we have a lot of vendors trying to give us tools that aren't necessarily open. They may not run on our chosen operating systems. There's little influence from the research community. I'm not really in the research community anymore, but I feel that I'm expressing frustration on the behalf of researchers. They have trouble getting stuff they need to do research, where in research you really need access to all the nuts and bolts, and binary blobs are a problem. More increasingly, SDR is getting a lot more influence from the open source community, largely through GNU Radio and some other open projects. So where in the past, SDR has sort of been this nebulous thing that was expensive and the barriers to entry were very high. We've now got low-cost SDR hardware, as low as $25 if you want to buy these receive-only DVB dongles. So the ability to build your own radios has really, the accessibility is just tremendous. And the research and education community really likes open source. It makes it easier for people to duplicate your work, extend your results, and all of this, build on the work of others. So we're going to give a little bit of background on what we're talking about. We're going to talk a little bit about the Keystone board. Then we'll have this vision for where we think we can go with software radio, and a little bit of resulty type stuff. So the wireless world is exploding. We've now, everyone in here probably has a radio. Actually, you probably have about 3 or 4 radios in your pocket. You got a cell phone with Bluetooth, with wireless, cellular uplink, NFC, and all of these radios, basically what they're doing in your cell phone is they're bolting together several different radios. Chances are the radios may or may not be from different vendors and things like that. So there's just a lot of interoperability and coexistence issues, sharing spectrum amongst radios. It's getting complicated. The backhaul situation is difficult. There's a story I heard about a guy looking, they have a tour of a cell tower outside of Blacksburg, where I'm from, for the wireless classes. And basically the operator says their company has a fiber backhaul for their cell tower, but they prefer to use their wireless backhaul, because if the fiber tower goes down, the fiber backhaul goes down, they have to call another division of their company to fix it, but they can fix their own wireless backhaul. So they're using wireless to get data to the tower and back down from the tower, just because it's easier than calling another division of the same company. And so the infrastructure, computing sharing, I mean, there's just been a lot of work in how to do all of this better. And the bottom line is, we need to be more agile, we need solutions that scale better, we can move code between things faster, and all these things that we know about. And so what's happening is, the standards are evolving faster and faster. I mean, we've been through GSM, UMTS, Edge, blah, blah, blah. I mean, alphabet soup of cellular standards. And each time, the operators end up having to replace vast amounts of hardware. I mean, yeah, it gets done in software, but the software, reuse is always a problem. Guys just like to rewrite stuff all the time. So you have low reuse. Time to market is becoming a problem, and the mobile terminals themselves are, the life cycle of those is so short. So you have a lot of just, I mean, it's hardware, but some of the agile software techniques would really help the operators. So software-defined radio, what is it? It basically, in the good old days, we had a hardware-defined radio. And radios were built out of resistors and capacitors and inductors and transistors. So you would build a radio and it would then last for 20 years. I mean, I'm sure you've all got AM radios in your cars. I mean, these haven't changed in 100 years. I mean, there have been incremental improvements, but the basic technology has been the same. And they've done that for 100 years. But there's really no flexibility in your car radio. It basically is an AM radio, and they add new stuff. If you have a 20-year-old car, I mean, they've got digital subcarriers on FM now that you can't read, and there's no way to upgrade your radio to take advantage of improvements in radio services. So what we see here is we have speed efficiency, where if you go to a hard ASIC, you'll get reasonably good power efficiency and reasonably good speed, but you have zero flexibility. And on the other end, you have the GPP, which is basically a blank canvas for doing signal processing. And in the middle, we have the FPGAs and the DSPs, and I'm sure that the FPGA and DSP guys would like to argue which is more flexible and has the better power ratios, and I did not make that graph. And I will let you guys go out in the hall and argue which of your technology has better power flexibility trade-offs. But the key thing with software-defined radio is we're taking the resistors and capacitors that we used to use, and we're now doing those functions in software. And I don't have this slide in here, but my favorite ever software-defined radio slides is a guy showing the evolution of radios. And this was given by an antenna engineer. And he basically showed, the radio, more and more of the hardware going into software. The end picture is an antenna, an analog to digital converter, and a computer. And his punchline, of course, is the only thing that didn't change in all of that is the antenna. That's why you should become an antenna engineer. And of course, the analog to digital converter feeding the computer is ridiculous because there's real-world issues that come up. But that's what we're looking at, is how to basically maximize our ability to use the various pieces of technology to their best strength so that we can take advantage of power efficiency versus flexibility as best we can. So I should talk a little bit about GNU Radio because I'm not talking to a software radio audience. Basically, this is free software, GPL, FSF project, so copyright is assigned to the FSF. Website at GNUradio.org, and it's an environment for rapid prototyping and testing. I would also say that you're perfectly willing, people will deploy working solutions based on GNU Radio. I suspect the audience this slide was written for had a slightly different mentality, but I mean, it's a fully functional framework for doing software radio. Has good library of modules, sources, measurements, display blocks, and provides access to pretty much all the popular front ends and probably some unpopular ones. And if you have a front end that's not supported, go ahead, write your own blocks, and we can support it. So basically, this says Python script to control the creation of the waveform. So what happens is the signal processing blocks are typically written in C++. If you want, you can write them in Python, which is very convenient for rapid prototyping. Performance may suffer. And they're using Python to instantiate the blocks, but the flow graph basically all runs in C++. So one of the common misconceptions with GNU Radio is it would execute code in Python. But it is possible to build a radio that only uses Python to set up and tear down connections. And that's and it also is possible to build pure C++ radios with GNU Radio. I just want to make sure this slide doesn't create confusion that GNU Radio is running in Python. And the key part in GNU Radio is this scheduler that basically is deciding when the blocks run. So what is happening is data is flowing from block to block, and the scheduler is controlling what blocks execute. And all of this runs on top of POSIX OS. Basically, most people run Linux, OS X, and Windows are actually supported. The OS X support is reasonably good. The Windows, it works. But I don't think there's many knowledgeable people using it on Windows, but people do try to provide binaries so that people can get work done on Windows. So what we're showing here is that the data is flowing from block to block. The communication method, which unfortunately I don't have a slide on, is basically the blocks end up sharing a piece of memory. And the scheduler is maintaining read pointers and write pointers for the blocks. So basically it knows where the read pointer is and the write pointer. And when it has enough information for the block to run, it will call the block and tell it to run on so many items. And then it will return, pointers get updated. And the way those buffers are done, it basically uses a double mapping. So what it will do is, based on the number of input items and output items of the blocks involved, and the rate change inside the block, it will allocate a buffer as some formula that I forget. So you'll have like tens of pages allocated as a buffer. And if you have a 5-page buffer, what it will do is we'll allocate 5 pages and then map that 5 pages afterwards. So what you can do is you can start writing up to the length of the buffer, and you don't have to pay attention to the sample count. It'll basically wrap via the MMU. And this saves you calculation time. And I just wanted to highlight that a little bit because that is sort of a problem that we haven't really solved with this coprocessor work. GNU Radio Companion is basically your friendly GUI interface that makes it much, you don't have to write the Python script to instantiate the blocks and connect them. And this basically increases accessibility tenfold, hundreds of fold for people to start writing radios. Now, I will warn you, just because we have a graphical thing that you can drag and drop blocks, you still have to understand how the radio works. And I won't sugarcoat it. I mean, software radio can be quite hard. The math is difficult and painful. So just because we have this nice block thing doesn't make it easy. But it makes a lot of the boring tasks easy. So where are we going? TI has this Keystone 2 part. I mean, they always come up with these interesting pieces for software radio. They don't seem to aim them clearly at this market. A little bit about that in a bit. I mean, I started doing master's work looking at OMAP 1s and was always excited by the DSP, but could never figure out how to make it work. And we have a picture as a fan. I guess the quad A15s like fans. You've got your standard drawing of a SAW quad A15s, which are really nice. You've got a lot of DSPs. These are specialized DSPs with floating point. You've got 6 megabytes of shared RAM. And we have a bunch of coprocessors here. This part is actually oriented at wireless markets. So you have coprocessors, a rake accelerator, Viterbi decoder, FFT accelerators, turbo. These accelerators are basically designed to help do modern wireless standards like LTE. So this is very interesting. And so we're very interested in the problem of we have these interesting signal processing bits, and GNU Radio has traditionally been a solution for doing GPP-based work. And we're like, why should we stop there? I mean, let's use these interesting bits and use them to accelerate GNU Radio. I mean, the traditional method of accelerating GNU Radio is run on a big, fast Intel machine that sucks lots of power and has many cores. So we get parallelism by having, multi-core machines of the same architecture. Here we have a multi-core machine. I mean, technically each of these accelerators counts as a core, but it's a core that only does one thing. So it's basically an ASIC. The DSPs are cores that are good at particular forms of algorithms, and we have 4 cores of general purpose processing. So these are all good at doing different things. I really talked about a lot of this. They have high-speed interfacing, communication accelerators. So what we're trying to figure out is how we can use a framework that was designed for doing GPP work to do not GPP work. So we have milestones here. So GNU Radio typically runs on one machine and you just add cores. So you could take another machine with the same architecture and now distribute work across it. Then you can separate the block processing code out, have a common language, and use that common language to move your algorithms into different, basically what we're trying to do is a pathway to make it easier to develop code across the DSPs versus the GPPs. And what we need is a unified scheduler. You saw that GNU Radio is scheduling threads for each block. Now we want to schedule tasks running in DSPs and run the accelerators, the fixed accelerators. And if you have an FPGA, basically the FPGA becomes sort of like a hybrid between the ASIC accelerators versus the DSP accelerators. The DSP is probably easier to reconfigure on the fly, even though the FPGA guys might argue with me. But I would say that in today's technology, it's going to be easier to reconfigure the DSPs. So we have 6 DSPs that we can run an arbitrarily large number of blocks. Or I could have an FPGA coprocessor that had a number of fixed things, but I could reload the FPGA to change them, which is a little bit slow. So there's been a lot of work done in the area. Al-Fayez did some work with OMAPs. There's been some work on GPUs as well. This part doesn't have a GPU, but obviously if there was a GPU there, we'd be interested in harnessing it. There's a project at Virginia Tech called Greasy, which is GNU Radio made easy, which moves blocks into the FPGA. And at the last year's GNU Radio conference, there was a talk about using DSPs with GNU Radio done at Sandia, and that was on the a PCI-based board in an Intel machine. So they had a different sort of sharing, different way of looking at, yeah.
So are your they all FFT unit code?
Excuse me?
The coprocessors, you have all FFT unit code?
I mean, we've done FPGA coprocessors. Guys have done that for Summer of Code last year.
For your architecture, your diagram, they all FPGA diagram?
Yeah, I don't have anything on FPGAs in this talk because it's really focused on these guys' Keystone work, but I just want to mention it as something that is also going on in the background as well, right? We don't want to lock ourselves in to any one coprocessor solution. We need to get to where we basically have GNU Radio dealing with whatever clever ideas the silicon guys come up with.
Keystone 2, one chip.
Yeah.
Those coprocessors.
Yes.
Basic on that chip.
Now there's a PCI interface that you can hang an FPGA off of and then have, the ultimate solution. This slide is basically showing, the evolution of SDR and DSPs, and I looked at it and don't like it. And eventually, of course, we get to wireless in the cloud. I had to put this slide in because Vuk used to do cloud-based base station work. But really what we're trying to do is get more SDRs out there, and they can start to work together, and you basically are getting very close to a cloud of SDRs and all these great things that come from that. So a little bit more on the details. The ARM and the DSP, they both have caches. And I think the next line is supposed to say the DSP caches can be reconfigured as cache, SRAM, or a mix. So I'm pretty sure that slide needs to say DSP. There's 6 megabytes of shared memory, and there's no consistency between the caches, so there's no cache snoops running around to keep things coherent. And remember what I was talking about earlier is GNU Radio is basically using pieces of memory to move data between blocks. So the more you share that you have access to the memory from the DSPs and the coprocessors, it basically makes it easier for GNU Radio to treat you as a thread and not as an external blob. So for the GPU type solution, you basically have to ship all the data into the GPU. And also for the PCI-based DSP, they had to have ingress and egress blocks to ship data on and off the DSPs. With this architecture, what we're looking at is we think we can do one where there's no data shipping, which is a big win. So basically the concept here is you're either going to stream memory in and out of your coprocessors. So GR-DSP both had to stream data over PCI. So one was going to a DSP board on a PCI bus, one was going to a GPU. Greasy streams over Ethernet. It basically, what it is doing, has an FPGA attached via an Ethernet. So it would do the control in the GPP and stream data in and out of the FPGA fabric over Ethernet. GNU Radio Zinc would stream over the AXI. The AXI actually functions as a memory control. You basically have pretty good access to the memory, so I would argue that the Zinc solution is basically a shared memory solution, much like the Keystone. And the Keystone 2, basically we have tools that all of the coprocessors can share memory, which means no copying stuff around if we fix some things. And this is basically showing what Shen-Ho has done to date. He has basically been able to run accelerators inside the DSPs by moving data in and out of the SRAM. We're using the SRAM and various memory things to make it work. And unfortunately, I haven't had enough time to sit with him to really understand what he has working, but he has actually bits and pieces of it's working. We also have right now what he has working is basically maps dev mem and starts peeking and poking. And obviously he's looking at things like remote proc and things and worrying about that. And the key thing here is he's also using, looks like he's using UIO to get the interrupts. So issues getting the GNU Radio scheduler going is, the DSPs don't have MMUs, so they're having to go to physical addresses. We don't have cache coherence between the cores, which means you're going to be sharing through memory. We need a centralized scheduler to basically orchestrate all the signal processing and get the orders in places. And really the key thing here is we're viewing the DSP cores as funny-looking threads from Linux, which the DSP guys may or may not like, but if it sells Keystones, what do they care? So one of the things he's been trying to do is avoid the use of proprietary software at a very extreme level. So some of the problems, he's basically doing bare metal on the DSPs. And apparently doing bare metal on the DSPs is TI has assumed that you're using DSP BIOS, so the documentation at that level apparently is painful. And you kind of have to worry about clock domains and power control and things.
I have to say DSP BIOS is BSD license.
Yes, yes. He basically did make a note that if this was asked, it is BSD licensed. He was confused earlier. But still, he's interested in the bare metal problem. Yeah, if you don't want to use it, it's fine. You know, you have funny grad students that like to do everything themselves. More power to them. He's also using GCC 482 with the C67 whatever backend, which TI did a few years ago so they could get UC Linux running on an earlier Keystone, multi-core Keystone. And you know, so basically what he's looking at here is he was looking at the code generation, which apparently is okay but not perfect. So it's missing an easy optimization in this slide, and I'm not even going to pretend to understand TI-DSP lingo. But you can basically do open source work on one of these TI-DSPs without binary blobs, which for people that have been through OMAP 1 and that history, you know, it's been painful. So he's got tool chains, he's got libc, libems that he's built up. There's a thing called liquid DSP done by another guy when he was at Virginia Tech that is a basic signal processing library. He's got an ARM lib to control the DSP cores, and I made him put all the code on GitHub. Not well organized, but it's there for you to look at. So if you want to get a Keystone board and start playing with this, we'd love to talk to you. This is some of the work that he's either got in his to-do list. Orc is it's basically a language where you can write your signal processing in it, and then it will basically retarget it based on the SIMD instruction set behind it. And so you have all these algorithms written in Orc, and it basically will get you like 80% of the performance on various SIMD subsets without recoding. So conceivably, you could make Orc generate DSP code as well, and then reuse the Orc that's already been done. And he needs to get more of the GNU Radio blocks, you know, set up. And we'd like to get more platforms. I mean, one of the big issue that we face right now is we need to get GNU Radio to stop copying stuff in and out of the accelerators. And that is really one of the goals for this summer. And I've been beating on the GNU Radio maintainers to basically be more open to people wanting to play with the guts. They're terrified of people playing with the guts because it's a piece of code that works, it works well, and nobody wants to touch it because it is integral to the entire thing. But we really need to get some motion there to do some really cool things. And the primary contact on this is Shen Ho. He has code on GitHub. If you want to build GNU Radio for the Keystone, Meta SDR, the open embedded layer, I have a repo script for using repo to suck down all the various layers. It does suck down Meta TI, so you should be able to build for the Keystone EVM. And basically, the point of this talk is the Keystone part is a very interesting part for exploring accelerators in open source. So do we have any questions? Yes?
Has much art using supporting signal to time radio, for example, radiation detectors?
It occurs to me that there is, and I think there may be a talk. If you go look at, there was a track at FOSDEM this year on software-defined radio, and I believe there may have been a talk on exactly that is. Unfortunately, I wasn't in the room during that talk, but I think I'm trying to say some collider collection back end, but I may not be right. Yeah.
Well, that would be great.
Yeah. That's kind of what I'm thinking, but I just don't know. I mean, I would just look at the FOSDEM talks and see what there is there. This year. Yeah.
So what's your market? The radio right now, it's a commercial literally.
Yes.
So when you say define, software define, you define fluency, maturation, and stuff.
I mean,
are they?
Basically, software-defined radio, you're getting samples from an antenna. So you have, basically it's a representation of some piece of the electromagnetic spectrum, and you can do whatever you want with it. So you basically can sit there, identify signals, demodulate them. I'm only going to talk about the receive case, but the transmit case is basically the same. You can create your signals and transmit them. I mean, you can basically do anything you can do with the radio in software within the limitations of the hardware's ability to do math. I mean, obviously, you're not going to run a Wi-Fi access point on an ARM9. But with the right amount of hardware behind it, you can pretty much emulate any reasonable wireless standard. Yes?
So it strikes me like this is basically a data flow problem. And when you're doing that from a general purpose CPU, and stuff like that.
Yeah, general purpose processor.
Yeah, so when the deadline scheduler was it was exactly for this on purpose. So are you utilizing this or
GNU Radio basically just assumes that it's fast enough. Okay? Vuk had worked on a project called Allo where he was worried about figuring out how long blocks took to run and worrying about scheduling in that method. GNU Radio basically just assumes the brute force method of scheduling.
Yeah, so I mean, like, the deadline schedule that here was that is like proceedings of all the others.
Yeah.
Sort of happens.
Basically, GNU Radio tries to run the real-time scheduler. But the general assumption is if your waveform doesn't run today, it will run next year on the next generation of Intel hardware. This was sort of the early development model, is PCs were getting faster and faster. I mean, there's a digital TV waveform in GNU Radio, and it used to not run real time. You basically would record your TV show to disk and then run the flow graph to demodulate it. And I saw a note, somebody's actually started to work on that again, and it's almost real time. And this is over a period of like 5-6 years, some unit of time where processors have gotten faster and have more cores. I mean, when GNU Radio started, it was a single core. It was basically a single threaded scheduler. So it would only take advantage of one core, and this became ridiculous as the number of cores exploded. So it had the multi-threaded scheduler. And what we're talking about here is extending the multi-threaded scheduler to heterogeneous processors. So we don't care what we're running on.
So to some extent, Phil, this is why the bullet in one of your early slides about GNU Radio's great place to prototype things is still kind of...
Yeah, well, it's...
Because the difference between a prototype and something that volume production is exactly that. Optimizing the hardware resources that not have lots of capability.
Yeah, this goes back to Tim's talk. It's basically, do you have a general purpose solution, which is a software-defined radio framework, or do you basically hard code everything to maximize, eke every ounce of performance out of the hardware?
The answer, of course, is yes.
Yes, exactly. I mean, you're trading off time to market versus 100% utilization of resources. And the nice thing, of course, about open source here is we have a framework that we can start to modify to solve problems that they did not even think they were going to have to solve in the first place.
If you look at sensitivity issues and problems with aliasing on the HDDs and overloading of the HDDs, you don't need some RF filtering.
Okay, so you're asking the real question of dynamic range, and yeah. Obviously, you have to know about that and you have to pay attention. But that's basically, you worry about that at the digitizer level. One of the reasons software-defined radio is hard is people will create a flow graph and they won't pay attention to the gains and they'll immediately drive things nonlinear and nothing will make any sense. So yes, there are important real-world issues that need to be dealt with. Yes?
So you basically have a distributed flow graph problem.
Yes.
So NSN published a
an API called Open Event Machine.
Okay.
That's aimed at this problem. So just as a note of prior, and there is a port of that implemented for Keystone. And BSD license. I can't tell if your goal is to avoid proprietary software or avoid vendor but there is an implementation for Keystone and it includes BSD. So at least you might want to take a look at it.
Yeah,
See how they're exchanging.
Yeah, I should go and look at that. Might have to get you to remind me. I mean, I think there was some confusion with the DSP BIOS license, and to a certain degree, I think there's a sense of avoiding vendor software because it just drives us insane. And I'm not going to single out TI with that. It's like all the silicon vendors are equally guilty. So, I mean, it gets annoying sometimes. I work with some other vendors' software that also makes me insane.
Well, I think bias is not plastics.
Yeah.
I mean, plastics.
Oh, that's okay. He's doing bare metal, so this is quite the entertaining exercise. Yes?
Brought it up. What is the DSP BIOS license?
I don't know. You would have to go ask Bill later. Yeah. It's a BSD license, yeah. Yeah. Okay. Any more questions? Yes. The slides, yeah, I have to figure out the mechanics behind that, but I will put the slides up. And I may add a link to how to build GNU Radio for this as well. And that's actually my piece of work, and I didn't get it in the slides. Yes?
So if someone wanted to contribute, how could they get a hold of some Keystone hardware?
You would contact your TI representative. They haven't given me one, but I can cross the street and look at one.
So it's all eval kits right now. It's not like someone else is making hardware that you can go buy from.
Yeah, there's I mean, basically they're working with an EVM they got from TI, and I'm assuming that we can connect a usurp to it fairly easily, so we can get real samples in and out and things like that. So I mean, basically you can do real work with it. Anyone else?
What's the price point that TI is charging?
You would need to ask a TI person. I think I know the number, but I don't want to say it in front of a TI person.
I looked at the website the other day. Using the 900.
Well, it all depends on your. It's all relative. Cost of SDR hardware is all relative. Some of us remember back in the past where it's tens of thousands of dollars and more.
And is there any overlap with the USRP? I showed up late. You may have already discussed.
Okay, no, I didn't talk about that at all. Basically, what you would do here is you would get your favorite piece of your favorite digitizer and attach it. It's got a GigE port. It's got a USB port. So you should be able to use all of the popular low-cost solutions.
Yeah, just as part of this effort, is there any development of some new and interesting blocks that are, hard to do in the GPP domain?
No, right now we're trying to get the mechanics, fleshed out. We've got a guy that's going to be Google Summer of Code, and I would say there's probably a lot more active work in the Zinc stuff as well. So we have to solve the general purpose the coprocessor problem. And once we get the distributed processing problem solved, then we get to do all the interesting stuff. And the Keystone is just a fascinating test case for this because it's got a variety of different accelerators on it. Anyone else? Are we done? And feel free to catch me afterwards. Okay, thank you all.